Welcome to Electromagnetics playlist. Here in this session, I'll be going to explain example based on divergence theorem. And to have example based on divergence theorem, this is the question where we have been given with function f, that is xy in I direction plus yz in y direction plus zx in z direction, with value of a is equals to 1, b is equals to 3 and c is equals to 2. So you can see the geometry of cube where a, that is there in x direction, so that is having value 1, b that is there in y direction and that is having value 3, and c that is there in z direction and it is having value 2. So we are dealing with to determine volume integration of divergence of function f, and we are also dealing with to determine surface integration of function over this surface. And as per divergence theorem, both of these functions should be same. So here we are dealing with to verify divergence theorem by calculating both of these values, and both should be equal. So here we will solve both of this, but one thing that I would like to suggest all of you, see, whenever this type of question is coming, at that time you should prefer this method. By taking divergence and taking volume integration, you can easily solve this problem. You should not go by this calculation f dot ds, right? So this close integration of surface, so that will take very long time to have a calculation of this, and it requires accuracy even. So I prefer this method. By taking divergence and volume integration, directly we can be able to calculate this surface integration even. So both of these are same as per divergence theorem. Let us solve this problem by considering this case, del dot f volume integration. So see, first of all we need to calculate divergence of function f. So divergence of function f del dot f. So divergence of function f, that is del by del x of fx plus del by del y of fy plus del by del z of fz, where fx is coordinate of function in x direction, fy that is coordinate of function in y direction, and fz that is coordinate of function in z direction. So if you place that, then you will be getting, see, del by del x, fx is xy, fy that is yz, so del by del y yz, and z component is zx, so del by del z zx. And this is what partial differentiation. So y is constant, take it outside, and differentiation of x is 1, so this will be y. Here z is constant, del by del y, that is 1, so this will be z, plus here x is constant, so del z by del z, that is 1, so this will be x. So this divergence, that is y plus z plus x. Now we need to take volume integration of this, and for volume integration we have variation of x, y, z coordinate, where x is varying from 0 to a is 1, means x varies from 0 to a, and a is 1. Y varies from 0 to b, and b is 3, so y varies from 0 to b, that is 3, and z varies from 0 to c, that is 2. And now as if we calculate this, so that is del dot f, that is y plus z plus x, and here there is triple integration where x is varying from 0 to 1, y varies from 0 to 3, and z that varies from 0 to 2. Now let us have integration of this with respect to x first. So if you do this, with respect to x integration, then y is constant, so y into x, plus z is constant, so z into x, and x integration is x square by 2, and limit of x that is varying from 0 to 1, dy dz. Now if you place this limit where x varies from 0 to 1, then when you place 0, this will get 0, but when you place 1, so this will be z varies from 0 to 2, y varies from 0 to 3, and this is x is 1, so y plus z plus 1 by 2, dy dz. Now we need to integrate this with respect to y. So if you integrate this, see z varies from 0 to 2, and integration of y, that is y square by 2, integration of z, that is y into z, and integration of half, that is y by 2, where y varies from 0 to 3, dz. Now if you place y is equals to 3, then some function will come, and if you place 0, this will get 0, right? The reason is y is there in each term. So if you place y, then you will be getting, this is 9 by 2 plus 3z plus 3 by 2 dz, right? Now see, 9 by 2 plus 3 by 2, that is 12 by 2, which is 6. So we can say z varies from 0 to 2, 3z plus 6 dz. And if you do this integration, you will be finding this is 3z square by 2 plus 6z, where z varies from 0 to 2. If you place 0, it will get 0, but if you place 2, this will be 3 into 4 by 2, so that will be 6 plus 3, 6 into 2, that is 12, so 6 plus 12, that is 18. So basically this volume integration, that is 18. So this is 18. Now see, this has to be 18 even, but now I'll explain you how to calculate this step by step. So we will do this for each surface one by one. So let us consider this surface, outward surface, that is the first surface. So I'm writing it here. This is surface number 1, and for this surface, x that is equals to a, and a is equals to 1. So for this first surface, I'm writing it over here. This is surface number 1, and for that x is equals to a, and that is equals to 1. So we can say dx is equals to 0. And on this surface, if you observe this y, that is varying from 0 to b, and b is 3, so we can say y that belongs to 0 to 3. And if you see the variation of z, then that is varying from 0 to c, where c is 2, so we can say z belongs to 0 to 2. And direction of this first surface, that is in this direction, so that is there in x direction, right? So here we can say this surface ds, that is dy dz in x direction. Now if you calculate this surface integration for first surface, you'll be finding, see, f dot ds, right? Then if you observe this function f, then here see surface is there in x direction only. So this is only the coordinate, x coordinate, that will come in the picture. So you can say surface integration means dy dz, where y varies from 0 to 3 and z varies from 0 to 2, and this dot multiplication, that is having only x component, and that x component is xy only. So here xy dy dz. Now here x is equals to 1, you can take it outside as a 1, and here this y and z, those are independent, so we can take separate integration here. So here y integration is y square by 2, limit is from 0 to 3, and z integration, that is 1 integration is z, limit is from 0 to 2. And if you place this 1 into 3 by 2 into 2, so if you do this, 9 by 2, 1 into 9 by 2 into 2, so 2 will get cancelled and this will be 9. So surface integration of this first surface, that is 9. Now similarly, if we calculate surface integration for this surface, right, let us say this is surface number 2, this one. So in that case, for this second surface, here x is equals to a is equals to 0. You can see for this surface x is 0, and as if x is equals to 0, dx is equals to 0, where same thing, like see, y will vary from 0 to 3, z will vary from 0 to 2, ds, that is dy dz in ix direction. So surface integration, that is 0 to 2, 0 to 3, xy dy dz, as only ix component is there. But if you place x is equals to 0 in this, right, you'll be finding this surface integration will get to 0. So here this f dot ds, that is this only, but where x is equals to 0 for this surface number 2, so this will be now 0. Now let us try to calculate surface integration for this third surface. So let us say this is third surface, so I am writing it surface number 3. Now see, for surface number 3, here this y is constant, so y is equals to b, and that is equals to 3. So I am writing it 3. So dy is equals to 0. Now here x will vary from 0 to a. So I am writing it over here. X belongs to 0 to a, and a is 1. And z will vary from 0 to c, and c is 2. So we can say z belongs to 0 to c, that is 0 to 2. And ds, that is dx dz, and if you see this surface number 3, so that is there in this direction, that is y direction. So I am saying, see, this is what in iy direction. Now if you do this integration f dot ds, then in this f dot ds only y component is there, right? So that multiplication will be yz only, this only, right? All other component will get 0. So this double differentiation, where x varies from 0 to 1 and z varies from 0 to 2, and this dot multiplication, that is yz only in iy direction, right? So yz dx dz. Now here y is equals to 3, so we just need to place it 3 into z integration, that is z square by 2, limit is from 0 to 2, and x is actually having one coefficient, so integration of 1 is x, where limit is from 0 to 1. Now if you place this 3 into 4 by 2, so that is 2 into 1, so 2 into 3, that is 6, so integration of this will be 6. Now if we calculate this surface integration for fourth surface, and let us say this is fourth surface, right, opposite to 3, so that is this, and on this fourth surface y is constant and y is 0, you can see. So here if I place y is equals to 0, so dy is equals to 0. Now again over here x is varying from 0 to 1 and z is varying from 0 to c, that is 0 to 2, but if you see the direction, that is there in iy direction, right, that is there in iy direction. So iy direction is having this component yz, where y is 0. So if you place y is 0 in this, then you'll be finding this is f dot ds, where y is 0. So this will get to 0. Now let us calculate this problem for fifth surface. Now I am considering this as a fifth surface, right, and for fifth surface you can see here z is constant for this surface, so z is equals to c, and c is equals to 2, so we can say dz is equals to 0. Here x is varying from 0 to 1, so x belongs to 0 to 1, and y is changing from 0 to b, where b is 3, so y belongs to 0 to 3, and this surface ds, that is dx dy, and if you observe this surface, that is there in this direction, that is there in z direction, so into iz direction. Now if you do this integration f dot ds, then this dot multiplication, that is resulting into z component only, right, the reason is surface is having only iz component, so this dot multiplication, that will be zx. So we can say here this is zx dx dy, where x varies from 0 to 1 and y varies from 0 to 3, and z is 2. So z is 2, it is constant, let us take it outside, into x integration is x square by 2, it is varying from 0 to 1, and y is 1, so its integration is y, which is varying from 0 to 3. So if you place this 2 into half into 3, so that is 3, and for sixth surface, that is opposite of fifth surface, if you do same calculation, you will be finding here for this sixth surface z is constant, and that is 0. So here z is equals to 0, so dz is equals to 0, and here same thing is there, x varies from 0 to 1, y varies from 0 to 3, and direction is there in iz direction, so this component will be zx only, iz component is zx only, where if you place z is equals to 0, this surface integration, that will get to 0. So now we have calculated surface integration of all 6 surfaces, right? So if you add all this 6 surface integration, then first surface is having 9. So if you add surface integration, then that is for first surface it is 9, for second surface it is 0, For third surface it is 6. For fourth surface it is 0. For fifth surface it is 3. And for sixth surface it is 0, so that is 18. Right. So you can see our answer is 18 over here. So both are same. We can say here we can verify divergence theorem. But I think one should understand this. You should not do this much big calculation for 6 different surfaces. I think you should go for this divergence theorem calculation, and easily one can be able to calculate volume integration as well as one can be able to calculate surface integration. So in difficult problem, you should go by divergence theorem. It will give you easier way of calculation. I hope that you have understood this session.